The paper of the day is HOT, a height optimized Trie index for main memory database systems. It's a 2018 paper. The paper presents the height optimized Trie, a fast and space efficient in-memory index structure. The core algorithmic idea for HOT is dynamically vary the number of bits considered at each node, which enables a consistently high fan-out and thereby good cache efficiency. The layout of each node is carefully engineered for compactness and fast search using SIMD instructions. Their experimental results, which use a wide variety of workloads and datasets, show that HOT outperforms other state-of-the-art index structures for string keys both in terms of search performance and memory footprint, while being competitive for integer keys. They believe that these properties make HOT highly useful as a general-purpose index structure for main memory databases. Now let's look at the evaluation. The evaluation is based on the YCSP benchmark and a wide variety of workloads and data distributions. They compare the following state-of-the-art index structures. First, ART, the adaptive radix tree, which is the default index structure of Hyper. It features variable size nodes and selectively uses SIMD instructions to speed up search operations. Second, Mass-Tree. Mass-Tree is a hybrid B-tree/Trie structure used by Silo. BT, the STXB plus tree, represents a widely used cache-optimized B plus tree and hence a baseline for a comparison-based approach. The default node size is 256 bytes, which is in the case of 16 bytes per slot, 8-byte key and 8-byte value amounts to a node fan-out of 16. And the fourth is HOT itself, which is a C++14 implementation of HOT using AVX2. Now coming to benchmark, their benchmark configuration corresponds to the 6 YCSP core workloads. The workloads are listed here. The first one, A, we have 50% read, 50% update. B, 95% read, 5% update. C is read only. D is latest read with 95% read and 5% insert. E is 95% read scan, accessing up to 100 elements with 5% insert. And finally, 50% read and 50% read modify write. Each workload is separated into two phases. The load phase inserts 50 million keys in random order into the index structure to evaluate. In the transaction phase, 100 million operations specified by the workload to be evaluated are executed. Each benchmark configuration is created in two variants using a Zipfian and a uniform distribution to select the records to operate on. Each of these benchmark configuration is created for 4 different datasets, 2 string datasets representing long keys and 2 8-byte short keys datasets. Now, looking at the contributions of the paper, they presented the height optimized Trie, which is a novel indexing structure that adjusts the span of each node depending on the data distribution. In contrast to existing Trie structures, this enables a consistently high fan-out for arbitrary key distributions. Furthermore, HOT's compact node layout enables efficient search using SIMD operations. Their experimental results show that HOT is 2 times as space efficient as its state-of-the-art competitors, that is B-trees, Mass-Tree, and ART. That it generally outperforms them in terms of lookup and scan performance, and that it features the same linear scalability. These properties make HOT a highly promising index structure for main memory database systems. Now let's give this paper a PS score. Overall, it's bumpy read with some super dense parts because of the code, so it gets 7 out of 10 on readability. With 14 pages long, it scores 8 out of 10 on length. Reproducibility and repeatability shouldn't be too challenging, so it gets 8 out of 10. Industry value and learning meter is decent, so it gets 8 out of 10 and 9 out of 10 respectively. Overall PS score is 8 out of 10.